everyone, welcome to the fourth video on bonding series. We have dative bonding to talk about today. By the way, the full video is on YouTube at Copy Chemistry. Today we're looking at dative bonding, and I think the first thing I would like to say is that dative bonding is also called coordinate covalent bonding. In the last video we talked about the ordinary covalent bonding, so this is the coordinate covalent bonding. Alright, so now coordinate covalent bonding looks like covalent bonding because the type of covalent bonding. Remember what happens in covalent bonding? Two atoms would contribute electrons and then they will share it equally. But for coordinate covalent, also known as dative bonding, one of the atoms would give that electron and then both of them will share it. You see that? So that means that for dative only one is contributing. That's what's happening there. So we have examples of dative compounds, which is coordinate covalent compounds. For example, NH4 plus. We also have NH3BF3. These are examples of covalent compounds, NH3O plus. So I'm going to do this one, and this should be BF3 by the way. BF3, NH3BF3. The name is a particular compound, yes. The name is ammonia trifluoroborane. So you want to write that clearly. Ammonia trifluoroborane. That's because your borane is supposed to be B with HHH like this. 4 of them, that's your borane. So if you have ammonia here and then you've substituted like this, instead of having hydrogen, it is now called a trifluoroborane. Okay, so that's how it works. Now let's look at how it works in ammonia. NH4 plus. This is ammonium ion, not ammonia but ammonium ion. So we're going to look at how it works in ammonium ion. This H3O plus is your hydrozonium ion. Hydrozonium ion. By the way, if you have any questions, you can leave them in the comments and we'll check them out. Right, so let's see how this works in your ammonium ion. We already looked at the way ammonia works. Formation of ammonia, that's your NH3. So we saw that it's a covalent compound, and we also saw that ammonia has 2 lone pairs. Do you remember? So we have our nitrogen here with our 2 lone pairs, and then we have a hydrogen, we have a second hydrogen, and we have a third hydrogen like this, having 2. Okay, so eventually we have 8 as a total, but then there are 2 lone pairs like this. So this is our ammonia. Now our hydrogen should be this. This should be hydrogen, right? 1 electron. But what does it mean for you to have H plus? The plus here means you've lost 1 electron. So let us lose that 1 electron, and that will mean that this stuff here will be empty. Okay? So if we've lost the only electron, then it's going to be empty like this. So this is our H plus. So what could happen is that this H plus could combine with all this, such that this just comes in here like that. So you can see that it's only the nitrogen that is contributing the electrons, but then they are sharing it equally. So now our H plus that's supposed to be here has 2 electrons, is balanced, and then our nitrogen here is fine. So eventually this is your NH4 plus. So you can look at it this way, that you have your NH3 like this, and there's a bond to the last H plus, but then this is the way I'll do it. I'll put the arrow like this. This is showing that the person or the atom that's contributing is the nitrogen. Okay, so nitrogen is the one contributing. That's why the arrow is like this, pointing towards the H plus. So if you see something like this, you can also say that this is a representation of the dative bonding. Right, so let's look at our ammonia trifluoroborane and see how that works there. On your own, you would do the one of H3O plus, ammonia, and your ammonia trifluoroborane together. So we definitely have our BF3 first, and then it will come together. So if this is our BF3, remember that when BF3 is being formed, you would have a deficiency of electron on the boron, and that's because boron exhibits this exception to the octet rule. Remember we said that for the octet rule you need to have 8 electrons, right? Yes. So there's always an exception to some of these rules in chemistry, including the octet rule as well. So you could have these ones that would have like limited octet. This one just has 6 electrons, because you can see that there's 3 bonds here, right? So eventually that corresponds to 6 electrons around the boron. For instance, if you were given your sulfur now, sulfur could have more than 8 electrons, could have up to 12. Phosphorus could have up to 10. Okay, so these are exceptions. Normally we're supposed to have 8. Yes. So these are exceptions. Now I could have that last electron that comes, that stays here in your nitrogen, being contributed, and then it bonds up with your boron there. So that means we're going to still have something like this, right? And that would be the connection. So this is basically what we have. You can decide to draw the shells and put the electrons there where necessary, and you'll still have pretty much the same thing. So this is dative bonding, and that's how it works. So you would check out this one. Please work on this, and let's see how you do. Alright, so the other thing I want to say about the dative bonding is that it also works like the covalent, because dative is a type of covalent. Okay, so as per the characteristics, it will be similar to that of the covalent. Okay, it might not be all exact, but then it will be similar. Alright guys, so I'll see you in the next video, where we'll talk about the intermolecular forces, the hydrogen bond, metallic bond, and the van der Waals force. Right, bye.